Welcome to Chapter 6, Properties of X-rays. This is Maureen Julian. The theme that I've set for this, the fun theme, is X-rays of animals or plants. What I want you to notice that this is very different from the diffraction of X-rays that we'll be talking about in this chapter. These are contact shots, so to speak. The turtle is laid on the X-ray, and it's the absorption. We're looking at the absorption of the various bones and shell of the turtle. So that is very different from looking at the diffracted beam, which we'll be describing in detail. Okay, the chapter objectives are to discuss the discovery of X-rays, the principle of superposition, constructive, destructive, and partial interferences, Young's double slit experiment, the property of electromagnetic waves, X-ray spectrum, Bremsstrahlung and characteristic X-rays, absorption and X-ray tubes and filters, X-ray diffraction, Bragg's law, the powder diffraction camera, and finally the synchrotron. The exercise for the chapter will be on the picture from the powder diffraction camera, the famous fingerprinting use of X-rays. I like to think of the discovery of X-rays going back to the Crookes tube, which was founded in the middle 1800s, and it was the first time you got a vacuum of 1/1,000,000th of an atmosphere. Now this opened the doors to a number of experiments, because what you could do here was you could insert into this vacuum tube a cathode and an anode. The anode is connected to the positive side, the cathode is connected to the negative side, and if we close the switch and put on a voltage of about, say, 40,000 volts, what will happen is that the electrons will boil off the cathode, they'll zoom across to the anode and make the connection, and a number of experiments can be done with this apparatus, the famous E/m experiment from your physics days. Now, there's another thing that happens when you close the switch, and that is as the electrons slam into the anode, X-rays are given off at the anode, and the X-rays will depend on a number of things, one of which is the composition of the anode, and we'll be discussing that. This marvelous discovery was made by Röntgen about officially in 1895, and it was an extraordinary discovery and led to an enormous number of consequences. Now, in order to study X-rays, we have to look at the properties of waves, and here's a ocean breaker. That's the end of the wave. And here's another example of a wave, which is a heart wave in an electrocardiogram. And well, here's a simple wave, a sinusoidal wave, specifically cosine, and we have the wave is a function of the distance and the time, and here we have the amplitude of the wave, we have the wavelength, we have the distance, we have the velocity of the wave, the time of the wave, and we have a phase angle. Okay, now if we have our amplitude of 5, we put the 5 where the A is, and we produce this equation here, produces this graph. So you can see at t equals 0, at x equals 0 and t equals 0, of course, the amplitude is 5, and we have the wavelength is going to be, what is the wavelength? Well, it's 2 pi divided by lambda, and in this case it's going to be 1. So we look here, if we go from here to here, we're going from here to here, which is a length of 1. I want to point out to you that you can start any point of the wave, say here, and you have to go to another part of the wave to get the wavelength of identical neighborhood. So we come along here. Now this has the same height, but the neighborhood is certainly different. So we have to come all the way over to here. So this will also give you a wavelength of 1. If we have two waves, we can, and they have different amplitudes. Say the blue is this lower one, has amplitude of 5. The red has amplitude of 6. It's a little higher. And when we add them together, and notice they have the same angular part, we get this green wave, which is a constructive interference. The wave they get, in effect, the amplitude gets bigger. Now, if you are out by a half a wavelength, in this case pi, you have the blue, and then you have the, which is 5 cosine 2 pi x, and here and the red is out by another half wavelength. It's going to have constructive, the interference is going to be destructive, that is, it's going to cancel out totally, and here's our flat wave right across the green one. Now, most of the time we get partial interference, which would be, we get, it's a little bit off on both the angle and the phase, and so we get an attenuated wave such as this green wave. And that's what we're dealing with in Bragg's law and in our X-rays. Now let's look at a really simple example, and that is Robert Young's double slit experiment. Robert Young was a physician, and he was interested in, he was an eye doctor, I believe, and he also gave Young's modulus as this same Young, and he did this wonderful double split experiment where you have a source and you columnate the wave. If you just have one slit, you're just going to get the wave coming through like that. Now if you have two slits, an amazing thing happens, and that is that if you look at the projection of the area of the place right between the two slits, you're going to see that you have a bright fringe there because you're getting constructive interference. If you come over here at this point, you can see you're getting also constructive interference, and in between those two constructive interferences we're going to get destructive interference, and we get a dark spot. So what we're seeing is the zero order, which corresponds to this point right here, and then the first order fringe is, which are these two, which corresponds to top and bottom here, etc. Now here's the little bit clearer diagram. Here's the bright spot, two bright spots. Here's the angle theta, and here's r, which is the distance between the two slits. So we can see that there's a reciprocal relationship between the angle in which you can observe the bright spot and the distance between the spots. So it's actually between the r and the sine of theta, and it's going to be a constant. That product is going to be a constant because it's equal to the wavelength, and so the bigger r is, the smaller the theta is, and vice versa. Let's look at a specific example. Here's red light, has a wavelength of about 6,500 angstroms. If we have, say, m equal 1, and if our distance between the two slits is 13 microns, or 130,000 angstroms, it's about twice as big, we're going to get an angle of approximately 3 degrees. We can see that angle of 3 degrees. However, if we have r, and we now have 1 millimeter, we have a rather large distance here, then the angle is going to get a whole lot smaller, and we simply can't see an angle of 0.003. So in order to get an interference pattern, the spacing between the slits must be of the same order as the wavelength of the radiation. And in effect, that's going to be true of the crystal as well. Now, if we look at our Crookes tube, And here we have our electrons. We're going to look at the voltage across the tube. We're going to look at the composition of the anode, and we're going to look at the filters. Now, first of all, the properties of the wavelengths. We can see the X-rays are down around 10 to the 18th frequency with a wavelength of 3 times 10 to the minus 10th. And here's my energy in joules. And you can see that the energy is increasing as we decrease our wavelength and increase our frequency. Here's a pictorial of the electromagnetic spectrum. If you're talking way down here, you're talking about wavelengths about the height of the Empire State Building. Here's a wavelength of about 5 or 6 feet. And now we come down here and we're into X-rays, and that is around the atomic level, and that's what we're interested, because we want to see the difference between the atoms. And so we'll look at, first of all, the different radiation. Let's talk about the voltage. So we have the voltage causes the electrons to leave the cathode and slam into the anode. Here's the kinetic energy of those electrons. It's EV, and it can be also written as Planck's constant times nu max, or Planck's constant C divided by lambda min. So if we want to find out the minimum wavelength, we see that it's a function inversely related to the voltage that we put across the tube. So if you multiply HC divided by E out, you get 12,398. And so this is the proportionality constant given, you give a certain V, and that'll give you your lambda min. So let's look at that. For example, if we have 10 kilovolts, we're going to get a minimum wavelength, say here. Now, if we increase the number of kilovolts to, say, 20, then we're going to decrease the wavelength that we pick up our spectrum. Another thing we could change would be the target. Now, if we hold the voltage constant and we change the target, it's not going to change the threshold, but it will change the height of the intensity for a given voltage. And you can see here, as you increase the atomic number of the element that the target is made up of, then you get a more intense beam. So here we have the nucleus. We have, as we fall back, say, from the L to the K shell, we can get a photon of K alpha, X-ray photon of K alpha, and that superimposes upon this what we call Bremsstrahlung, this almost background radiation. And this is a case of a nickel target, for example. A nickel target will have the K alpha at 1.66 and the K beta at 1.55. Here's the K beta. And it's these very columnated beams, in effect, that will give you, is what we're using to pick up the X-ray diffraction spots. Okay, and if you look at various elements, here's the increasing atomic element, here's the specific element, and here's the K alpha and the K beta, and you can see that's a decreasing function there. So this is a very, very important relationship. This is Moseley's relationship for the K alpha and K and L alpha lines. We plot the atomic number versus the square root of the voltage, of the vibrations and frequency, and we get a straight line. Now, this is the first definitive proof of the ordering of the elements in the periodic table. It was, for a while, there were a couple of elements. They weren't sure which way they came because of various chemical problems, but the Moseley's relationship definitively defined the ordering of the elements in the table. So all you have to do is, which is a pretty big deal, Moseley went and made different targets of all these different Z numbers, and then he plotted these various relationships here. And this is a very good exercise for you to do, and you can do it for extra credit. I will give you the specific information in a separate file. Now, the other thing that we have to think about is absorption. Now, in those pictures of the turtle with the bones, we are talking about absorption, but also the beam, the diffracted beam, when that goes through matter, it is modified by and absorbed by the matter. So we have the initial beam coming out, and we have a lesser beam coming, the initial beam going in, and the lesser beam coming out, and here's the material, and it's got various thickness. So the absorption depends on the type of X-rays. That is, are they copper X-rays from a copper target or nickel from a nickel target? What are the physical properties of the material? That is, this material here, is it a protein? Is it a metal? The thickness of the material, the thicker it is, the more absorption you're going to get. And here is the formula. The I coming out is equal to the initial intensity going in, and here's the distance, and the mu is the linear absorption coefficient, and the linear absorption coefficient is proportional to the density of the material. Therefore, you can divide through the mu by rho by the density, and you get a constant. So this constant is independent of the state of the matter. It only depends on the material itself. And for example, oxygen in gaseous or oxygen as part of a compound would, like H2O, the mass absorption coefficient would be the same. That is, here we have it. And so we tend to write this formula for the absorption as a function of mu over rho, and then of course if we divide through by the density, we've got to multiply that out up here. So here's the atomic number, and here's rho over the density, and notice this is an increasing function. And for the copper, if you have for the K alpha radiation going through a material of atomic number 24, 25, etc., notice we have an increase here, and then we have a drop off here, and that's a very important concept, which we'll see here in the next slide. This is the absorption edge, and here is the case of copper. So copper comes up, and then it hits the absorption edge, and then it starts over again, and it'll hit another absorption edge, etc. Molybdenum is slightly different. It will have, here's its absorption edge on the same scale, and it will have a drop off here, and it will again have this same type of behavior. And we can also, there's a relationship of mu over rho is proportional to the cube of the wavelength of the radiation, the radiation that's impinging, and the z of the material is proportional to the cube of the z. And this, there are a number of little interesting problems you can make up with that. Okay, now let's look at our X-ray tube. Here's the Crookes tube, and essentially the modern day tube, you simply, or what in effect you're doing is you're putting your finger here and you're pushing the tube such that the sides of the tube are sticking up, and you're pushing the cathode and the anode to be much closer to one another. And then you get this tube that's like this, And that's a safety device, among other things, because you can't get your finger down in here to electrocute yourself with this 30,000 volts. So here's my cathode, here's my anode, here's the x-rays coming out, here's the windows that the x-rays are going to come through. Here are the windows over here, and the x-rays, of course, are coming out all around, but only 4 ports are selected. And this is very high voltage, so we need to have a water cooling system. And if you have high electricity and water, you better have a very well-designed system, which they are. And the third thing that we want to bring up was filters. You have the Bremsstrahlung radiation, this so-called white radiation, and superimposed on that you have the characteristic radiations. And what we're really interested in is selecting out one and getting the pattern from this one particular spike. If we have the 2 of them here, we're going to get 2 different sets of diffraction patterns slightly off from one another. And that can be, some people don't like that, so it has good uses too. But you can get rid of this K beta by filtering. Here we have the filter. We put in a nickel filter on a copper target, and you can see you cut out the K beta and you let the K alpha for the most part in. Here's a picture of zinc blende. You're going down the 3-fold axis. This is one of the very earliest pictures, and you can see they don't even have a beam blockage. And here's coming down the 4-fold, so you can actually really see those symmetries in the pictures. The Lowry equation is a form of Bragg's equation. The crystal acts as a 3-dimensional grating, and the waves are emitted by the radiated atoms, which have a single frequency. And here we have the incoming S0 and the outgoing S, and here's the distance between the two atoms, so to speak, or the repeats. And here you have this equation, and each diffracted beam has 3 integers, and those integers are going to be H, K, and L, and they are the Lowry indices. Bragg's law kind of combines the 3 Lowrys into one. Both laws are useful, and they're essentially the same thing. Here we have the red incident ray coming in, the blue diffracted beam, and if you're going to get constructive interference, you have to have this phase angles equal to this phase, these phase. So this extra distance has to be an order of wavelength. So this extra distance is going to be 2 times D, H, K, and L, and we have this sign of the angle here. So here's the D spacing here, the D of H, K, L, and then there's the theta, and then this side over here is D sine theta, and we have 2 of them, so it's 2 D sine theta, and together they have to accommodate an integer number of wavelengths for this extra area, extra distance traveled. If you want to think of the Bragg's law, you can think of it this way. The lambda is the X-ray part, that's the energy part. The D spacing is related to the crystal, and only the crystal. The crystal has a specific D spacing, and the theta is actually you, it's the observer. So you're really part of this equation, and you can see that this, again, you have the 2D is and sine theta actually are multiplied together to get a constant. The bigger the D, the smaller the theta, and vice versa. Here's a picture of an X-ray diffraction camera, a very simple photographic one. The film is around the edge here, and we've undone it. We've flattened it out for sodium chloride, aluminum, and calcium fluoride. You can see there are different lines here, and you have the incoming beam, you have the crystal is at some sort of angle here, and the angle theta of the incoming beam is going to be the same as the diffracted beam, but the relationship between the diffracted beam and the undeviated beam is going to be 2 theta, and 2 theta is called the diffraction angle. So another way of going back, remember we have 1 over d squared is equal to HKL G star of, and HKL like this, and we have done that in chapter 5, and we'll be using that when we put together the diffraction pattern. So here we have Bragg's law. We solve it for sine theta, we take the arc sine, and then we double it to get the diffraction angle. And in your exercise for this week, you're going to have to go to Mercury, and for your own particular pattern, this is caffeine, and you'll get, I will explain to you in the video how to find that. And here's the picture, the film, the picture that you'll get, and this is the one calculated in your book. These little sides here are artificially put in. There is no, that's just to make it look like a real one, or this is a manufactured one. This is just generated from the data. Okay, another type of radiation is synchrotron radiation, and here's the Cornell synchrotron picture. This is a mile across. You can get very, very high energies, and so you can do very complex proteins. Here's a protein of over 15,000 non-hydrogen atoms, which could never be done any other way except by a synchrotron. And that's all, folks.